You know, when we talk about fairness in AI, it's really easy to get lost in all the technical jargon. But what we're really talking about isn't just code or math. It's a story. It's a story about us. It's about how our own blind spots, our own history, can get soaked up by these algorithms, amplified, and then handed back to us with this stamp of seeming objectivity. Okay, let's get into it.
46.8%. Just let that number sit there for a second. That's the percentage of young black men in Los Angeles County between 21 and 24 who've been entered into a police gang tracking database. Almost 1 out of every 2.
So, yeah, how does a number like that even become possible? That is the big question we're going to investigate together. Because a statistic like that, it doesn't just appear out of thin air. It's the end of a long chain of events, of human choices and automated systems. And we're going to follow that chain from the street all the way into the machine.
But before we dive into the tech, I want to ground this in what's actually at stake. This isn't just about abstract data. This is Craig Lewis. He was in school, he said he was building the perfect life, and then he was swept up in a huge gang raid, spent 2 years in jail, and was finally let go because, well, there was no evidence against him. We're talking about real lives, real families, and real futures getting completely knocked off course.
I want you to just picture this for a moment. It's the middle of the night. Suddenly, there are over 700 police officers executing no-knock warrants. Families are being woken up by armed officers in full riot gear. Young men are arrested under these really broad statutes where, whether you're guilty or not, it feels like the safest bet is just to plead guilty to avoid an even worse sentence. This raid, this is the real-world impact that flows from the data and the systems we're about to pull apart.
So, how do we get from a raid in the Bronx to a biased algorithm? Well, here's the most important thing to remember. Machine learning models, they aren't magic. They're basically just reflections of the data we feed them. So if you want to understand the output, the prediction, you absolutely have to start with the input. The data is our first and biggest clue.
And even before we touch a line of code, we run into this really fundamental problem. What does fair even mean? Turns out there's no single answer. On one side, you have this idea called demographic parity. Its goal is equal outcomes. So a bank using this idea would have to approve, say, 10% of loan applications from every single group, no matter what. But on the other side, you've got predictive equality, which is all about equal error rates. It says the model should be just as likely to be wrong for one group as it is for another. And here's the kicker. These two ideas are often at odds. You usually can't have both.
Okay, so you're facing this tough choice, this trade-off, and a really tempting idea comes to mind. It's a logical one, right? If you're worried about an algorithm being biased based on race, why not just remove the race column from the dataset? Don't let the model see it. Problem solved?
Well, that perfectly logical idea leads us straight into a classic trap. It's actually got a name, fairness through unawareness. And it's a perfect example of a solution that seems simple on the surface, but can make things so much worse.
And here's why it's such a dangerous trap. The algorithm might not be able to see a column that's literally labeled race, but it sees everything else. It sees your zip code, which, because of a long history of segregation, is often a very strong signal for race. It sees past payments, what high school you went to, your marital status. All of these things are proxies. They're clues that allow the algorithm to piece together and effectively rebuild the very information we tried to hide. Bias, it turns out, finds a way.
And all of this, it brings us to the absolute core idea of this whole explainer. When we take this messy, biased historical data and feed it into a machine, it doesn't just learn the bias, it transforms it. It learns to predict where we've looked for crime in the past, not where crime is actually happening.
Let's just walk through how this cycle works, step by step. It starts back in the 80s and 90s. We have aggressive policing tactics, like the hammer sweeps in LA, that result in tens of thousands of arrests, many for tiny offenses, and they're heavily concentrated in minority communities. Fast forward a bit, all that arrest data, which is a record of policing decisions, remember, not a perfect record of crime, gets digitized. Then, today, that historical data is used to train a predictive policing algorithm. The algorithm chews on the data and learns the pattern. It says, hey, a lot of arrests happen in these neighborhoods. And what's the result? It sends more police right back into those same communities, which leads to more arrests, which generates more data, feeding the cycle all over again.
And believe me, this isn't just a theory. Look at the famous Compass dataset, which is used all over the country to predict whether someone will reoffend. It perfectly shows this problem. The model isn't actually predicting if someone will commit another crime. No, it's predicting if they will be arrested again. And we've just seen that arrests are a function of where we send the police.
So here it is,
This is the click moment. The algorithm is a bias laundering machine. It takes these messy, complicated, biased human decisions from the past as its input. It crunches the numbers, and it spits out a clean, quantitative, seemingly objective prediction, a risk score, a hotspot on a map. The bias didn't go away. It just got cleaned up. It got sanitized.
So, is this whole thing just hopeless? Are we stuck building machines that just replay the worst parts of our history on a loop? No, not at all. Actually, the great news is that once you understand how the machine works, you can start to see where to intervene.
We can think about this in three main places. First, you can intervene right at the start, in pre-processing. This means you fix the data itself before you even train the model. You could, for example, reweigh the arrest data from those over-policed neighborhoods so it has less influence. Second, you can intervene during the training itself, in processing. This is where you actually change the algorithm's goals, adding a penalty if it starts showing too much bias between different groups. And third, you can even intervene at the very end, in post-processing, by adjusting the model's final predictions to make the outcomes more fair. Each one has pros and cons, but they give us levers we can actually pull.
But maybe the most powerful intervention is to just ask a better question from the get-go. Instead of just trying to predict arrests based on geography, what if we use data to really understand the complex social networks at play? This image here shows that kind of approach. It's about mapping relationships and influence, not just pins on a map. It's a move away from that blunt, biased data towards a much richer, more nuanced way of seeing the problem. It's about using data for insight, not just for automated judgment.
Whew, okay, we have covered a ton of ground. So let's try to boil this all down into a few core mental models that you can take with you, whether you're building these systems yourself or just trying to make sense of their impact on our world.
Okay, first, and this is probably the most important one, data is not reality. It's a flawed mirror of reality, and it's always shaped by the choices and the biases of the people who collected it. Second, fairness is a trade-off. There's no single magic fairness metric that fixes everything. When you choose to optimize for one definition of fairness, you often make things less fair by another definition, and that's a human choice, not a technical one. And finally, unawareness is not a solution. You can't fix bias by just telling your algorithm to close its eyes. The bias will always find a way through the proxies.
So we spent all this time talking about how to measure and fight bias, but that just opens up a whole new set of even deeper questions, doesn't it? I mean, it's one thing to make a model fairer, but how do we make it explain itself? How can someone like Craig Lewis ever challenge a decision if no one can tell him how that decision was made? And when the algorithm gets it wrong, and it will get it wrong, who is responsible? That's the next big conversation we need to have.